We know the role of a capacitor in a circuit is to store energy so that it can be used or converted to another type of energy, really, at a specific point in time. When we're charging a capacitor, work must be done by an external force, which is typically a battery. As more charge accumulates on each plate, it takes more work to move an element of charge from one plate to another. That should make some sense, because initially, when our capacitor is uncharged, it's really easy to move a bit of charge around. It's not being repelled by another negative plate. As the plate gets more and more negative, it's harder and harder to put more electrons on that plate. So we're going to think about what it takes to move a small element of charge, EQ. And when I say to move it, that means we're moving it from the positive plate, or from one plate at the beginning, to what'll be the negative. That means we're doing a little bit of work since we're only moving a little bit of charge. And we know work can be expressed as Q times the potential difference. So in this case, a little bit of work would be our potential difference times our little bit of charge. And we know for capacitors, capacitance is Q divided by delta V. And therefore, we could express this delta V as being Q over C, the capacitance. Now you can probably guess what we're going to do next. We're going to add up all the little bits of work, which means we're going to use an integral. So the total work that it takes to charge our capacitor can be found by doing the integral of Q over C dq. Now, we learned in class that capacitance is a constant value. Capacitance is something that is dependent on the geometry of the capacitor, not how much charge it has. So I could pull a 1 over C out of my integral, and then I just have the integral of Q dq. Now I want to go from my capacitor being completely uncharged to it being fully charged, and quite often we use a capital Q for capacitors that are fully charged. And knowing what I know about taking integrals, the integral of Q dq would be Q squared over 2. I evaluate that between 0 and Q, and I could find that my expression for the work that's done to be equal to Q squared over 2C. Now we know work is the same thing as a change in energy. And since it was work done by an external force, we could think of this as being positive change in energy. And we'll call this U sub C being the energy of the capacitor. Well, since we started out with it completely uncharged, it didn't really have any energy to begin with. So that tells me I could write this as the final energy of my capacitor is equal to Q squared over 2C. Now, using my equation for capacitance, the capacitance is charge divided by potential difference, I could write this equation in a couple of other ways as well. So, for example, I could write this equation as 1/2 Q times delta V, or I could write this equation as 1/2 C times delta V squared. Those two other versions are what's on your equation sheet. But again, knowing where those equations came from is important. A couple of other facts about the energy stored by a capacitor. It can be viewed as being stored in the electric field between its plates. That's where that energy comes from. That's why charges have a potential to move, is because we're setting up an electric field between the plates of the capacitor. One other fact. In a parallel plate capacitor, the electric field between the plates is uniform. Therefore, the energy density, and we know that density can be thought of as something per volume, is also uniform. And in this case, since we have a parallel plate capacitor, we're talking about the energy divided by the volume of one plate, which would be the area of that plate times the distance between the plates. This is what we're talking about when we say energy density here. We don't deal too much with energy density in AP Physics, but this is just a good fact to know and remember.